Hey, good morning, everybody.
Good morning.
Good morning.
Good morning.
I should just leave this going in the background as like a strange thing. All right, any questions?
The final's going to be 1 hour, is that right?
The final is an hour and 50 minutes. So almost 2 hours. It should say that on Canvas somewhere.
Yeah, sorry.
That's okay. All right. Well, I posted a tentative study guide, list of topics, and we'll talk about that later on today and also tomorrow. We'll go through that. But I want to finish up saying a few things about processes. This class final and CSE215 final are both on Monday, right? Let me double check. Because if I do this from memory and I get it wrong, then we're all doomed. So this is a 10 o'clock daily class, so the exam will be on December 6th, Monday at 10 o'clock. And then CSE 215, which is a 12:30 Monday, Wednesday, so that'll be 12 o'clock also on Monday. So yeah, this section of 224 and CSE 215 are back to back on Monday, so this coming Monday. And then if you're sneaking in here and you're actually in the 11 o'clock section, the final for that should be on Wednesday. But our exam will be Monday. All three finals on Monday. Yeah, that used to happen to me sometimes. That's good and bad. I mean, it's good because you get it over with, and but it does take a mental toll. So the 11 o'clock class, the final is on Wednesday. But you have to take the exam for this class if you're in this class.
Be in my seat for 4 hours.
Yeah, fun, right? I think my longest exam was 8 hours. That was a comprehensive exam when I was in graduate school at GW, and it was an 8-hour exam, and people brought, food and water and stuff like that. And it was 8 questions, so you had about an hour for each question. It was pretty intense, but it was oddly fun and satisfying. It was on computer science, so it was a exam you had to pass to get a master's degree. It was one of the requirements, and so it covered, a number of graduate level topics in computer science. It was kind of fun doing something like
horrible.
that. It was pretty good. Yeah, I can tell you some stories about it sometime. But it was good.
Assuming you passed.
Yeah, I survived. It's kind of a going the distance sort of thing.
Was it involved writing programs, or was it?
Yeah, you had to write programs, but there was also a lot of theoretical stuff. It also included like circuit design, so stuff like we do in Engineering 250. It was sort of
Verilog?
no Verilog. Yeah, that wasn't a thing. But designing a CPU or a part of a CPU or things like that. It was good. The nice thing about finishing exams, it leaves you with kind of a sense of accomplishment, even if you don't ace it. It's like if you compare it to what you could have done before you took the course, it can be encouraging just to see like how much stuff you've actually learned. All right. So let me talk a little bit about pipes. And we know that in Linux we can do something like, command 1 and pipe it into command 2. And the idea is whatever this thing tends to standard out goes into, some sort of pipeline, and what comes out the other side goes into standard in of this other process.
Hey Nick, quick question.
Yeah.
You just froze up for about 20 seconds there.
Oh, did I?
Did you call for attendance?
I did not.
Okay.
But yeah, people can do an attendance ping because everyone seems to be pinging anyway. So yeah, go ahead and do an attendance ping.
Would you say that'd be some sort of classical conditioning in the way that people automatically start doing attendance pings at the beginning and end of Zoom meetings?
Yeah, seems like it. I'm probably going to change. I'm either going to drop that or change it in winter. If I have a chance, I'm going to make a website that that people will go to and just click something for the ping. But it will only let you ping when I ask for a ping. It'll open for like 90 seconds. Just
Very
to
cool.
Yeah, but I probably won't get to that. So I may just ditch attendance. Yeah, so that may not be your internet that's acting up because someone said I froze. So maybe it's me, but I don't think I have anything weird going on right now. I got the usual setup. Let me see. Yeah, I'm just doing the usual. All right. If I like freeze for like a ridiculous amount of time or something, definitely let me know. And I can try. Well,
Your audio went out too, so I don't even know if you could hear us.
Did it? Okay. All right. Let me kill my camera because that's pretty optional. And let me see if that helps. All right, so pipes. So we have, a pair of commands, and we can connect them with a pipe, so the output of this command feeds the input of that command. How does that work? We know that we can run a command, right? And when we type C1 from a bash prompt, bash will use fork to make a copy of itself. It'll use exec to change that copy into C1. And if we're piping this into command C2, it will make another call to fork to create another copy of itself, and that copy will be told to change itself into C2. So now we've got bash, and we've got C1, and we've got C2. And we want these two processes to be connected somehow. We want the output of this to go to the input of that. And this is done through something called a pipe. I mean, we call this a pipe, but a pipe is something else also. So pipe is a low-level system call. Okay, it's in chapter 2 of the manual pages. And it basically gives you a pair of file pointers. So you call pipe, you pass it a 2-element array of integers, and it will populate these 2 elements with file pointers, which can be used to read and write information, but with one little twist. So this is definitely off the exam. I won't ask you about pipes or dupes or things like that. So this is sort of extra material, but I guarantee that whatever you get out of this lecture will help you down the road in the next year or two with other courses. So it's worth staying tuned in. So let's write some code. So let's make a child process. And if the call to fork returns a 0, then you know you're the child. Otherwise, you know you're the parent. And what I want to do is create a pair of processes. I want to have my original process, main, and I want to create a child process using fork. And I want to send some information to that child process. Right, so this might be, a process we're creating that's going to do some processing for us on the side, and we're going to send it instructions. And I want to just create a communication channel between our main thread and our child process. And if we can do this, then doing all the rest of everything that Linux needs to do, everything that Bash needs to do, is pretty much the same. But let's just look at this, creating a connection between threads. And this is in the general framework of what's called inter-process communication, IPC. And it's a topic we'll talk about in 223 in a fair amount of detail when we do this in Java. But let's see how this works in C. So I'm going to make a pair of file descriptors. I'm going to call it FD bracket 2. I'm going to say pipe FD. I'm going to create a pair of endpoints for a pipe. Okay, what's going to happen when I call pipe FD, I'm going to create some sort of conduit that looks like this. And FD bracket 1 is going to be something I can use to write into one end of this pipeline. And the other end of the pipeline, I can read what comes out of that with this file descriptor FD bracket 0. So if I just call pipe, FD will get populated with 2 integers, and we can look at what those integers are. So I'll just print out FD 0 and 1. Let's see how we did. Hey, not bad. So if I run this, FD 0 is 3, FD 1 is 4. And that's actually not terribly surprising, because remember when we run a program under Unix, we always have 3 file descriptors. File descriptor 0 is what we call standard in, file descriptor 1 is standard out, file descriptor 2 is standard error. And those are the 3 main input-output channels that we always have in a C program. Well, if I ask this call to pipe to create more file descriptors for these 2 endpoints of this conduit, right, they come back 3 and 4. Those were the next sequential file descriptors that were available. And if I called pipe again, the next 2 descriptors would be 5 and 6. So nothing too mysterious there. Alright, but once I make this call to pipe, I can basically write into FD bracket 1, right, which is file descriptor 4 in this case, and whatever I write into there can be read by reading file descriptor 0, which was a 3. So this is kind of like, if you wanted to send information somewhere, you can write it into a file on a hard drive, and another process can open up that file and read it. But that's a kind of goofy thing to have to try to do, because you have to deal with, how do I know if there's something in the file to read? How do I know if I already read this? This gets the same effect, but in a much cleaner way. If I write something into here, anything that's reading from this end will read that thing. And if it tries to read something else, it'll wait until something else gets written in. So you write this and it moves through the pipe and it pops out the other side. All right, so let's go ahead and make a child process. And if I'm the child, wait for a message from the parent. So we'll print something which says I'm the child here, I'm waiting for a message. And I'm going to read from file descriptor 0, right? Whatever value that corresponds to. And I'm going to do this with a read call. And so read is the low-level way to read from a file descriptor. It's the thing that fgets and getcar and fgetcar and all of those things use under the hood, right? So read is basically our lowest level way to read from something. And it takes 3 arguments: a file descriptor, a buffer, and a number of characters available in the buffer. Alright, so I'm going to do this. So here's what I want to read from, right? It's that end of the pipe. And I'm going to read into just some buffer. And I'm going to say I have 120 characters available. And I'll print out whatever I read from that pipeline, and I'll just exit. So this is where the child will go away. And on the parent side, let's just send a message to the child. So we'll say hit enter. We'll wait for the user to hit the enter key. And then let's go ahead and send something to the child. So we're going to write something into file descriptor 1. And we're going to do that using this low-level write function. So write looks just like read. We have a file descriptor, a buffer of characters, right, an array, and the number of things we want to write. So we'll write into file descriptor 1. We'll write hello \n, and I'm going to tell it to write 7 bytes. So I'm going to write HELLO, that's 5. The new line, just to make things look pretty, that's 6. And I also want to write the null terminator. And then I'll just have my parent exit. Alright, so you got the setup. I don't know if this is going to work, but you got the setup. We're going to create a clone. The clone, which is the child, is going to say, hey, I'm waiting for a message, and it's going to try to read from this end of the pipeline. This is the output end. When it receives something, it'll tell us it received something and tell us what it got. On the parent side, right, we're going to say, hey, I'm the parent, hit enter, wait for the user to type enter, and then send this string hello into the send end of the pipeline, at which point the child should receive it. And I honestly don't know if this will work or not. But it compiles. Alright, so parent is here, hit enter, and it tells us the child is here waiting for a message. Right, so both of these processes have access to standard out, which is my display. So whatever each of them says will get, potentially mixed up with one another. The parent is hanging out waiting for me to hit enter. The child is trying to read from the pipeline. So if I hit enter, the child gets a message saying, hey, child just received hello, followed by a new line, and everyone exited. And we can be a little more careful about this, because the read call will actually return an integer which tells you how many bytes you read. Right, so this return value is the number of bytes that you read, 0 if you hit the end of the file. So let's just go ahead and print out also child received %d bytes. Message equals. And let's see how many characters the child actually received when it read from the pipeline. So it says it received 7 bytes. Why did it get 7 bytes? Because that's what the parent wrote, 7 bytes. If I had only written 6 bytes, strange things might happen. So nothing broke, but we got the hello \n, and we happen to have a null terminator at the end. If I ran this enough times, that might not happen. Yeah, it's going to be well behaved just to be annoying. All right, so this is the basic way that processes communicate with one another in Unix, is through this idea of a pipeline. And if I want the child to be able to send information to the parent, what do? I create a second pipeline. So this pipeline is going from the parent to the child. I could create another pair of file descriptors to go from the child to the parent. And I could write into here, and the child could write into that second pipe. And now I have two-way communication. And the reason this works is because I made the pipeline before I said fork. And remember, once you say fork, the new process is a clone of the current process, other than the return value from fork. So the new process will have the same pair of file descriptors, and so it knows how to, write into the same pipeline that the parent is writing into.
So what would happen if you did it afterwards versus before?
If I do it afterwards, I should end up with two totally unrelated pipelines. Because the parent will be able to write into the pipe, but the child will read from a pipe, and nothing's ever going to get sent to it. So let me copy my print message too. Alright, so one of them said my file descriptors are 3 and 4. The other one said it was 3 and 4 also. That's interesting. Child here waiting for a message. Right, so the parent sent the message out, but the file descriptors 3 and 4 in the child process are different from those descriptors in the parent process, because they were created once these two processes had their own independent existence. So that's a little strange, but it does make sense. Alright, the other part of this, which I'm not going to go into, is something called dupe2. And you can look at the manual pages, and you'll definitely play with this later. But the other thing we can do is once we have, a conduit set up between two processes, what we can do is make a call to a function called dupe2 to basically say, hey, you know that thing that I used to call standard in? I want you to change that. I want you to change standard in to be this thing. And now this pipe is effectively going into standard in on this process. And any time that something in this process tries to read from standard in, it's going to now read from FD0, which is this end of the pipeline. And the parent process can do a dupe2 call, which says, hey, you know that thing I call standard out? I don't want that to be file descriptor 1 anymore. I want that to be this file descriptor. And now anything in the parent that writes the standard out actually writes into this pipeline. And if you do this, if you're bash and you do this for a pair of commands, you've got this pipe set up now. And whatever this process sends to standard out, you don't see on your display. Instead, it goes into this pipe. And whatever this tries to read from standard in doesn't come from a keyboard, it comes from this pipe. And now your two processes are connected together. And that's the whole pipe mechanism of Unix. Alright, so I'm not going to ask you about inter-process communication on the exam. Or about these file descriptors. Or read or write or things like that. We may dabble... Yeah, we may dabble with it somewhat in 222. But we'll mostly deal with these concepts in detail in 223. But we'll deal with them in Java. And in Java, these things are very easy to work with. Creating a new process is extremely easy. Sharing information between two processes is very straightforward. And then at university, you'll do these things in C at a very low level, and you'll get to deal with all of the minutia involved in that. Yeah, so like mutexes and things like that. Yeah. So that was, like I say, basically I just wanted to kind of give you some view of processes in Unix and sort of how they come into being and some of the basics of them. So let's talk about the final exam. So final exam, as we said, will be on Monday, 10 o'clock to 11:50. And it will be the same structure as the midterm. It will be a file that you download from Canvas or look at on Canvas, and it'll have a series of questions. You write up the answers to those questions and then turn that into a PDF and upload that before the deadline. If you have an extended time allowance, take whatever the extended time allowance is. There's no countdown to a due date on Canvas. If you don't have extended time, make sure you upload it by 11:50. If you have time and a half, upload it by 11:50 plus, half of 110 minutes. And Canvas will tell you it's late, and I'll ignore that, right? I'll use your time allowance. And make sure that you know how to type code into an editor in a way that doesn't, change your indenting and formatting and uppercase and abbreviations and all of that stuff. Find a plain text editor of your choice. VI would be a really good choice, right, since you're supposed to know VI at this point. But if not, something, Notepad, Notepad++, something that lets you control the formatting of what you type, and that will let you export to a PDF. All right. Let's talk about topics. And I haven't finished writing the exam yet, but here's a list of topics. So possible topics. And there's two parts to this course. There's two parts to the exam. One is, Linux, and the other is C. And Linux is Linux commands, concepts, things like that, and then bash programming. So you can sort of, I broke this out into three parts, right? Linux, Bash, and C. And we can just go through this in order, but if there's questions or things in particular you want to go over, we can talk about those in whatever order you like. But I'll just start from the beginning. So Linux, what commands should you know? Basic things that let you work with Linux, right? So echo for outputting something, cat to look at the contents of a file, copy to make a copy of a file, move to rename a file, rm to remove a file, ls, you should at least know ls-l to get the long listing with additional information. WC, which lists, how many lines, words, and characters are in a file, date, and probably a number of other commands that we use, every time that we're sitting in Unix and doing things, right? I expect you to know those. The textbook for this course is a Unix textbook, so it covers all of these commands. But if you have not been working in Unix every day that you're taking this course, you probably want to spend some time between now and the final getting familiar with Unix, so you don't have to look things up. And if I ask you 10 questions that require you to know, cat outputs the contents of a file, CP makes a copy of a file, you don't want to spend 5 minutes going through a manual trying to find the answer to each of those questions, right? If it's something you've been doing for the past 11 weeks, then, these will take you 3 seconds to answer. So make sure you're familiar with basic commands, basic ways to get around and operate in a Unix environment. Make sure you know Git. Okay, we've been doing Git for every assignment. We've talked about Git, so you should know the basic commands we've had to use for Git, which are git init to start a repository. We only did that once, but it's just git init, right? Git add, git commit to take changes and put them into your repository. Git remote add origin, I probably won't ask you about that, but just write down what that command is. We only did that once here, right? But you should know that this is how you take your local repository and in some sense link it to a remote repository like on GitLab. And then definitely know git push origin master, right? That's how you push your repository over. There's a lot of other things to Git that we've touched on, git pull and checkout and all of that stuff, but these are the main ones that you should definitely know. Alright, standard in, standard out, standard error. Those are those three I/O streams that we always have available when we run a program. There's always something that the program will read from, like when you do fget, something it'll write to when you do printf, and an additional stream we can write to that's different from standard out. It's called standard error, and typically that's where error messages go. And normally, standard in is my keyboard, standard out is my display, standard error is also my display. Let's see, roughly how much of the test is multiple choice? I don't know if there's going to be any multiple choice, but there will be probably half the points, maybe a little more, will be programming, and the other half, maybe slightly less of the points, will be short answer, fill in the blank. Could be a multiple choice maybe, or a matching or something like that. But about half of it will be, programming, half of it will be non-programming, so it'll be shorter answer, conceptual questions, which is where, these kinds of things come in. So normally standard in comes from the keyboard. If I run a command and I say less than file name, that redirects standard in, and now standard in is reading the contents of a file. And if I run a command and I say greater than some file name, now standard out is not going to my display, it's going into a file. And if I do greater than greater, it's exactly the same thing as greater than, except I'm appending to the end of a file. So greater than will actually zero out a file before it starts writing. Two greater than signs say append to the end of a file. And if I have two commands, I can connect them together with a pipe. That's what we were talking about today, actually, was how that works. But, we've used pipes throughout the course. If you don't know how to use these, if you got PA5 working by using temporary files with greater than, less than, make sure you know how to do things using a pipe. And it's it's just ls pipe into word count that tells me how many lines my ls command returned. And so date pipe into cowsay, my chi tells me what the date is. So cowsay by itself reads standard in, date by itself takes the current date and displays it to standard out. If I use a pipe, then the output of date is sent to standard in of cowsay, which means my cow is going to tell me the date. So that's your minimal test case for pipes. Alright, you should know about quotation marks. So in Linux, quotation marks, sometimes they don't do anything. If I say echo hello, it says hello. If I say echo quote hello, it says hello. If I say echo this is fun, or I say echo quote this is fun, it does the same thing. But quotation marks do have two functions. One is they group things together. So if I say vi, this is a test, I'm editing a file called this. If I say next, now I'm editing a file called is, and then I'm editing a file called a, and I'm editing a file called test. So vi, this is a test, tells me I have 4 files to edit. Right? I'm editing a file, a file, a file, and a file. If I say vi quote this is a test, I'm editing a single file called this is a test. And now if I do an ls, guess what? I've got a file called this is a test. So quotation marks will group things together. And that's about all they do. If I say echo quote $x, that $x is replaced by the value of the variable x, so it echoes hello. And that happens whether I do quotes or I don't do quotes. But if I do single quote $x, right, single quotes group things together also, but they also suppress this business of taking the $x and saying, let's look at the value of the variable x. So this is a way to make things a little more literal, which is what we mean by quotation marks usually. And that's probably the main difference between double quotes and single quotes. Double quotes will still do things like $x will get replaced, whereas a single quote will just give you, whatever you have inside. So that gives me 4. If I echo this in single quotes, I get $2 + 2. All right, and then back quotes are totally different. Back quotes are a way to say, hey, I want to execute a command and I want to capture the output of that command. So if I say x equals back quote date, that changes x to the output of the date command, which is very different from saying x equals quote date, where x is just equal to date. So back quotes say run a command and set x equal to the results of that command. And it's a one-time operation, right? This does not rerun the date command every time that I look at the value of x. When I did this command, the date command executed, which produced, this timestamp, and then x was set equal to that string. All right, and so we've talked a lot about shells. So what is a shell? It's a program written in C, by the way. It's a program that is running and for the most part waiting for me to type stuff and then doing something. And so if I type something like echo hello, it will output hello. And it shows me a prompt. My prompt is, a number inside angle brackets. On some systems your prompt is different, right? It might be your username and your host machine and a directory and a $sign, right? But it shows some kind of prompt and it waits for me to type something. And if I type something like, read X, this shell responds by basically sitting here and waiting for me to type, and then saving a variable value called X with that number 789. So now if I say echo $X, it'll show me 789. So one thing shells do is they interpret, commands like read and echo and pwd, which shows me my current working directory, and cd, which changes my current directory, so now I'm in a different directory. The other thing that that shells do is they execute commands that are part of the Unix system. And so, for example, if I say date, that's not a bash command. Date is a executable program sitting under the /bin directory. But if I type a command that bash doesn't understand, it will look for an executable program with this name, the name date. And if it finds it, it will execute it. And in this case, it prints out, the current date. If I want to know where date is, I can say where is date. It'll show me everywhere on the system that it knows something about date. If I say which date, it'll tell me exactly which date's going to be executed if I say date.
That's really cool.
Yeah.
You could do that.
Yeah, which is a useful command, because sometimes there's a bunch of versions of things. Not too bad on here. Let's see, if the shell is a program written in C, then that means when we code in bash, we're coding in a language within a language. That is a little bizarre, right? It gets worse. So Java is, written in C. And so when we write Java code, we're, compiling that with a program written in C. But these programs that are written in C are actually converted to assembly language and then assembled into machine code. And so, Java or Bash is, executing in a program that was written in a different language that was converted to machine code. And in some architectures, the machine code of the system is actually interpreted. There's actually a smaller machine inside the CPU called a micro machine that's written in a different language called microcode, and that microcode is interpreting the machine language instructions of the CPU. And so there's a whole hierarchy potential of how your bash instruction ends up affecting the transistors inside the actual hardware. There's languages that compile JavaScript now, true. And you can also compile Java. In some cases, there's things like just-in-time compilers and so on and so forth. It's C or C++, I don't remember which. So the very first Java compiler...
Regardless of whether or not it's C or C++, it's still C language, right?
Yeah. So this says first Java compiler was written in C with some libraries in C++. But then, of course, modern Java compilers are written in Java, which is what we do. GCC is written in C. Yeah, C is an extremely prevalent language. Windows is written in a combination of C and C++. Assembly, C, C++, MC script, JavaScript, other languages, compiler, JavaScript. Yeah, yeah. So yeah, it is very Inception. All right, so single quotes, double quotes, back quotes. What is a shell? So yeah, so that's what a shell is, right? It's basically this big C program that will let you execute commands, sometimes built-in commands, sometimes commands that are actually executable programs sitting somewhere on the system. So the shell we've been using is bash. Bash RC is a file that, if it's sitting in your home directory, contains initialization information. So if you always want to set up an alias, for example, you can put it in your .bash RC, and every time you start a bash shell, everything in the .bash RC gets executed. So my bash RC looks like this, right? It sets up my history size to be a few thousand. It sets up a bunch of stuff that I didn't set up. It gets rid of a lot of stuff because I don't like color prompts and so on. But my printer is annoying in that it's connected to the internet, and my system can't find it sometimes. When it goes into deep sleep mode, it disconnects, and so I have a wake command that will ping my printer by IP address, and when I want to print something, if it's not printing, I just say wake, and it will send a ping, and after a few seconds the printer will wake up and announce itself to the router, and then my print commands will find it. And so wake is just an alias. It's a shortcut for this, so I don't have to type this in every time I want to print. I can just say wake. When I want to scrape the attendance chance, I have a script called clean attendance. And I don't want to type in all of this every time I want to look at the attendance chat, so I just say clean. And clean is an alias for, running that. Here's an alias for a directory. When I want to change to this directory, I don't want to type in all of this, so I just say $SBIR. So you can put things in this bash RC file, .bash RC, in your home directory, and these things happen every time that you start a bash shell. All right, and so we'll talk about shebangs when we do programming, but that $ exclamation mark is the shebang. That's the thing that goes in the top of your script, but we'll talk about that down here. Aliases are just ways to set up one command that stands in for another command. So this final topics is going to be on Canvas, right? Yeah, it is. Yeah. All right, processes, which we just talked about this week. So what do I want you to take away from the processes? Basically, using an ampersand to run a job in the background. So if I want to do, GCC, blah, 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 a whole bunch of stuff that's going to take 10 minutes, I can put an ampersand at the end. And it will run this command in the background, but come back and give me control of my terminal. So, if this was a command that took 100 seconds, I can put an ampersand, and I can keep doing other things while that command is running in the background. Okay, it's the same thing as typing a command and while it's running, hitting a Control-Z and saying run in the background. So it's just a shortcut for that. Control-Z stops a process, but it doesn't kill it. And once the process is stopped, you have a few options. You can say BG, which says keep running in the background, which is what's happening now. You can do FG, which says run in the foreground, so now, it's as if I had just typed this command. And you can also say kill. And so I can kill it with either a process ID, or if I say jobs, I can see that, this is job 1. I can just say kill %1, and that'll kill it. Terminate it. And then just be aware that the PS command is a command that will show us processes on the system. And be aware that there are a number of switches, and I'm not going to ask you to memorize these switches, but PS by itself shows me processes I'm controlling. PS-L shows me more information. PS-username followed by a username shows me processes owned by the user. So just be aware that there's a variety of options, and you know if down the road.
Resume a process.
So FG will resume it in the foreground, BG will resume it in the background.
Okay.
Okay. And so you can always, you know, go to the man page for PS down the road if you need to do something in particular. But it's a long manual page, right? Because there's a ton of options. Alright, and fork, you should just know, you know, fork creates a clone of a process and it returns either a 0 or a non-zero integer. If you're the child process, fork returns 0. If you're the parent, it returns the process ID of the child. And more general concepts about processes, just the fact that, you know, everything that's running on your system is a process. And in Unix, we can look at processes and see not only the process ID, but the parent's process ID. And so we can form this hierarchy of, you know, where did each process come from? This was created by that process was created by this other process, and so on. And most of these processes were created when the system booted by, you know, some sort of grandmother of all processes, which is called a NIT. So just kind of, you know, general ideas. All right, so we'll start off with talking about file systems tomorrow and go through the rest of Linux, and then we'll review Bash programming and C programming. But, you know, definitely give this a once-over, and we can start with particular questions you might have tomorrow. Shoot me an attendance note, and I will see you tomorrow.